Uh, Hello. So I hope you have received all my emails regarding the electrical properties of graphene. Okay, and if you go through that all the papers, I hope you have gone through all the journals, all the literature and the reports. There are you feel that whatever discussion it's not that easy to it's not that difficult to understand that graphene related papers, right? Because all those things we already had a discussion some point of time, right? So it's not a great you don't feel like, I hope you don't feel like it's all the terms that really unknown, we don't know how to solve all those equations, expressions. It's not like still, the importance of the graphene or graphene-like material, like a graphene-like 2D material, that I'm not going to discuss. So please go through or Google it. You'll understand all this part. And whatever the papers I have forwarded you, that is the basis of your that today's discussions. Okay. Now you please go through all the papers, right, nicely, and the most critical part of these papers, that how to find out EK diagram of graphene. Okay, I hope that some of you might have understood how it has formed, but still let me discuss it more clearly. And the most important part, today's lecture will help you to understand not only about the graphene, it is also about how to apply whatever the theory we have studied previously, like how to solve or how to find out EK diagram. Okay, if a particular crystal structure is given. Okay, so what is the method that we are normally followed? You see, like we have, this is my Schrodinger wave expression, like E phi is equal to H phi, and we need to find out the proper eigenvalues of this matrix expression. And to find out the proper eigenvalues of matrix expression, I need to know that H component of each and component of this H matrix, the Hamiltonian matrix. Okay, so that is actually find, and how to find the component Hamiltonian matrix. That lot of methods are there. We already had a lot of discussion on it, but here actually we are doing something else. But the another good way to solve it, like you take a basis function, okay, and how to choose a basis function, like S, P, D orbits are there, no? So you can choose the best nice basis function, and it doesn't need that you choose always S, P, D all orbit, like orbital basis function or atomic basis function. So what you can do, you can go through the other experimental literature survey, and you can find an optimum basis function for this expression. And that's a good idea. And that's why that's the beauty of the empirical procedure, right? Definitely you can have a fast principle study, a fast principle procedure to follow all the component of H matrix. And empirical is giving a good amount of nice results. Okay, they're very close to your experimental result. Okay, so choosing a basis functions, eventually you can choose SPD. What's wrong in it? You can choose. There is no issue, because anyhow the number of matrix or matrix size is definitely less here, right? So it doesn't matter always, but still, if you can reduce the matrix, the basis component, that will give you more. What is called that? More. I feel that if you reduce the number of basis function, then you can really do the analytical solution nicely. Okay, so here actually that how you can do the matrix to basis function, the matrix expression, and this you can think about like how to transfer to the summation function, like that you need to solve it. If you have a two number of basis, so you need to have a two type of function, and this H matrix is 2 cross 2, that we already had a discussion on it, and this is the matrix expression, but that convert to the summation expression. And what is the solution? That is the solution again that we already had a discussion, and that thing we need to set it, we need to fit it here, we need to put it here, and then you will get a nice expression. It looks like this one. And finally, you will get MK, which is such a B cross B matrix, and this. Now the question is, what is the significance of B cross B? So that I think we can understand, like suppose it's a one-dimensional crystal array, and this is my crystal position. You see, it is not a kind of regular crystal lattice, no? Because what is regular crystal lattice or periodic crystal lattice? Like if you just choose any of the atom and the surround position of and the surrounding of all the atoms looks like same. Now here, if you see here this position, you see that you can see red here, but you see other red far away. That's fine. But the moment you see another lattice position, suppose choose this lattice position, you see that the environment is totally different from this atoms. Atoms see red here, but here this atom sees red far away from that. So it's not a actually periodic crystal or Bragg crystal, right? So what is the good way to do it? Consider a unit cell. And here, before you consider the unit cell, we name it the two atoms, like atom A and atom B, and AB, relation between the AB, we have the component of the AB, we have denoted T. Similarly, B to it, we have denoted T bar. And then another thing is that we have marked it like a unit cell. So now the question is, how many basis function here? Like here we can think about like each atom suppose having one basis function, then how many atoms are there in unit cell? 2 atoms. So that means each unit cell is having 2 basis function. Okay. So that means how many matrix we need to have? The MK matrix is 2 by 2 matrix, right? 4 components. Okay. Now, how this 4 component is coming? Where is the 4 components are coming? That also you can write nicely. But remember our old problem. Old problem is that we need to have a solution. Like if you have a n number of atoms, we need to have a solution by n cross n matrix. Now each one is having like 1 or 2 number of basis function. How many solution you need to have? 2n cross 2n matrix, right? So it's not like n cross n matrix, it's actually 2n cross 2n matrix. Now how we can represent this 2n cross 2n matrix? If you follow these rules, right? This is it's very easy to understand. Like suppose you if you try to form the H matrix, and how to form the H matrix, that we already had a discussion, the diagonal components epsilon, and then you find T1 matrix. The nice part is that you can group it. This is another group, this is another group. So like see, the diagonal, if you see the component, it is actually 2 by 2 by 2 by 2 by matrix. That is the beauty. So why the 2 by 2 matrix actually repeating diagonally? Because we have a 2 number of basis function. That means if you have a 3 number of basis function, we need to have a 3 by 3 matrix. So if you have a B number of basis function, you have a B by B matrix. And now this B by B matrix is actually recurred. And how many times we need to repeat it? We need to repeat it n times. So that means that is actually what NB by NB my matrix. So instead of repeating B by B matrix, here what we have done, we have chosen the n component of B by B matrix somehow with the summation method. Same like how we transfer the matrix expression to the summation matrix. Here what we have done, the B by B matrix which is summed over m component, right? And another thing is that look at those parts, like other component of the diagonal matrix, these are just nothing but transpose. Okay, so 0 0 T1 T1 0 T1. Okay, transport matrix. So that means we can easily write it. So again our goal is to form NB by NB. The size of the matrix is NB by NB. Now the question is, with this formula, can I get a NB by NB matrix? Yes, we can get. The beauty is that diagonally we are having B by B matrix, and if it repeats n times, so it is NB by NB. But then you can ask that again we are solving NB by NB matrix. So what is the benefit we are getting? Benefit is actually that we can easily write a program telling that, or you can easily writing a program about the how the H matrix looks, and H matrix looks diagonally same and other components nothing but transpose. So you can easily with a pen and paper you can write the H matrix without having any difficulties. That's it. So you may face some problem. Let's take an example of Graphene, and as I told you, though I already have shared all the documents, you please go through all the documents. The importance of Graphene, that also you please go through it. I don't need to discuss on these things. But what I am going to discuss here, the how to find a EK diagram of Graphene, applying all this theory. And I hope that will help you to understand whatever I have told. Okay. So the basic structure of the Graphene, it looks like this one. Okay. Now what I am going to do, I am taking a cart of this structure and see this is the cart, right? So I just take a cart and this is my Graphene of 3 things. So now we have to first find out, as a rule sir, that first two things that we need to find out: how many basis function per atom and what are the unit cell. So if you know the basis function, if you know the unit cell, you can easily write the matrix. Yeah? So first of all, how many basis function that we can consider. So carbon, the graphene, as you know, it's a carbon component. So this is carbon, this is carbon, this is carbon, all are actually carbon component, and the distance between one carbon atom to another carbon atom, let's represent it to A0. A0. Actually it is around 1.38 angstrom, approximately 1.4 angstrom, but you can write it actually A0. Okay. Now number of basis function. How to find out the basis function? Looks like that. Carbon, the number is actually 6. So how can you write the atomic number? Like 1s2, 2s2, 1s2 is fine, 2s2, and here px2, py, pz, right? So total 6, 1, 2, 3, 4, 5, 6. Okay. Then remember, we already had a last semester, and now even this current semester, we already had a nice discussion about valence. You saw the valence orbit or valence, what is called the valency, right? So you see that all of our electron transport and everything is happening, it's actually free electron, through free electron. And all three electrons, through free electrons, has as in their valence orbits, right? So here, so we have to just think about how many valence orbits are there. So this is my valence orbit, like 2 shells or 2 principal quantum number, 2st, 2px2, 2py, 2pz. Then how many basis function? For S1, px2, py3, and pz4. So always we need to think about the valence orbit. That could be our basis function, because for electrical engineering, because most of the electrons are actually free electron, try to flow through the crystal, through the valence position, right? Or what you can see other way, like whatever the electron exchange or chemical exchange is happening through the valence sites, correct? So in that case, so how many basis function we had? 2s, so 4. So this is actually good choice, 4. And that means B is equal to 4. So how many matrix we need to solve? B cos B. That means 16. The size of the M matrix is 16. And that M matrix I have to sum for M. M is the summation. How many terms we have to sum, and how to find out M, that I'll tell you. So idea is actually how to find out this basis function from that balance part. Second thing, find out the unit cell. Okay, and third one, we have to find out M. So M means how we are going to add or sum the position of nth atom. So we'll see. So that is good average, so we can start. But there is one thing. So since we are actually trying to understand the electrical properties of graphene, so people are saying, those people who did lot of experiment, they have said that you don't need to consider the other orbit S, Px, S, Px, Py. Pz is alone is fine. Now why? So one thing is that if you are not comfortable, you can start with 4 basis function and you can solve it. There is absolutely no issue. But since I am trying to solve it analytically on that PowerPoint board, so I think that let's consider one basis function, and that is Pz. Now if I say that it is having only one basis function with Pz just to solve analytically on the PowerPoint presentation, is it correct? It is also correct. Why? Because those people who did lot of experiment on that graphene based device, you understand, like, just go to our old problem that we have a two potential separation F1 and F2 through the contact, and if you fix this F1 and if you apply some voltage over there, so either F2 will change up and down, right? Or if you apply gate voltage over there, this whole potential will move up and down. That means we are really interested the energy states which are very close to F1 and F2. So far away, if some energy states are there, it doesn't matter. Why? Because even if you apply some voltage over F1, F2 or gate, it really doesn't cover all the energy states far away from the F1 and F2 position. Right? We are very much interested in those energy states which are very close to F1 and F2, not far away from F1, F2. And those people who did calculation taking 4 basis function, they found the energy states are far away, like 2s2, 2px, 2py. For this orbit, for this basis function, the energy states are here, and it is actually coupled. No? So you have something, so you get something up, something down. So suppose you have a energy level, so it is actually symmetry. Something you will get up, something you will get down. So that is it's actually 2s, 2px there and 2s, 2px there, but it's a far away. And the contribution of Pz, it is actually very close to F1 and F2. Okay. Again, I'm telling you, if you are comfortable over there, you can choose 4 basis function and you can solve it, absolutely no issue. You will get the same result if I choose Pz. Now, if you go back and check out all the journals and literature, you will see sometimes people are considering 4 basis function, sometimes people are considering 3 basis function, sometimes people are considering 1 basis function. And that depends on the choice, what type of properties you are looking. Suppose you are looking for electronic properties of this type of structure, I think only the basis function corresponding to Pz is fine. But those people who are really looking for optical properties, I think it's better to consider 4 basis functions. Okay, because it doesn't matter, because once you write a code, it can solve everything. But since I am trying to write on that paper or PowerPoint, so I go the nice result what people have already obtained, choosing 1 basis function that is corresponding to Pz. Okay, because that will help us to write all the expression nicely, and that also valid means because our target is to find out the properties of materials when you have a 2 contact F1 and F2, and we need to really actually looking for the energy states very close to that F1 and F2. So it's quite good results. Okay. Now 1 basis function 2 Pz with single atom. Okay. Now we have confirmed that number of basis function at the moment we are choosing 1 basis function. Right. Next stage is unit cell. Okay. Now before I start with the unit cells, this slide I have shown you several times. As I told you, what is called the periodic crystal. Periodic crystal means, suppose wherever you go, suppose you point these things, the environment is exactly the same. Suppose you go point these atoms, the environment is exactly the same. Or you can see that this is my atoms and you have another atom. So how to reach from this atom to this atom? It is like integer. So from here to here is a bar. So if you multiply h integer over here and then x y direction, you have to multiply k integer. You will reach over there. Integer means 1, 2, 3, 4. H is integer, k is integer. Like correct. Suppose you want to reach over here. So how to reach there? You go up to this part with some integer and then you go back. So that means 1, 2, 3, 3 into h. Sorry, 3 into a bar. Then you have to reach there. So 1, 2, 3, 4. And 4 into b bar. So h bar, 3 bar, 3a bar plus 4b bar. So that is actually, if you do this vector addition, you can reach it here aramse. So the concept, if you have a non-periodic crystal, what you have done? So what is the problem over there? Because it is, if you choose these atoms, the surrounding is not exactly the same. If you stand the another atoms like the red one, the surrounding of this atom and surrounding of this atom is totally different. So it is not a non-periodic, it's not a periodic crystal. And how to make a periodic crystal? You take a unit cell and that unit cell corresponding, you put this as a unit cell, and if you arrange this unit cell, this is nothing but a regular periodic. The nature of this unit cell plot mapping is nothing but a periodic, right? So it's essential to form that unit cell. So now our idea is like we have a basis function and each atom is having one basis function. Now this atom is fully periodic or non-periodic? It's actually non-periodic. You can understand the surrounding of this atom is totally different than the surrounding of this atom, right? Because here this atom is bended left side, but this atom is bended to right side. You can understand, right? Because the surrounding of this atom and surrounding of this atom may be same, but surrounding of this atom and surrounding of this atom is not at all the same. So that means it's a non-periodic cell. So what is our idea? Our idea is to make a unit cell. So what is the best unit cell that you can consider? So best unit cell you can consider. So what is the unit cell group so that it looks like a periodic? And this is the unit cell. So if you consider this as a unit cell, you can say it looks like a periodic. So what you have to do, you have to put it regular. So just like a previous thing, like you can put a single atom here, this part single atom here, this part single atom here. That you can do it as a homework, and that you can find out it's nothing but periodic arrangement. Okay, but what else? So now see, each unit cell is having 2 atoms. Okay, so that means how many basis function we have? 2 basis function, because one atom is having 1 basis function. Now each unit cell is having 2 atoms. So how many basis function? 2 basis function. So we have to solve the 2 by 2 curve matrix. Matrix 4. The matrix size is 2 by 2, right? 4 component we have to find out. Now there are few more things, not that easy. So that is actually overall my problem statement. So few more things we have to understand. So this is actually, you might have read all that, whatever journal paper I have forwarded you, that they have considered that this A1 and A2. It is like you have a unit cell, and what is the distance from here to here and what is the distance from here to here. So 2 distances are totally different. So this is A1 and this is A2. Okay. Now the question is, we have to find out the distance from this unit cell to this unit cell, and how to find out. Correct? Remember, from carbon to carbon distance is A0. So here I have written unit cell is having 2 atoms, and hence each unit cell is having 2 basis functions. And this is actually A0 because carbon to carbon bond is A0, so carbon to carbon distance is A0. Okay. Now we have to find out the component of A1. What is the A1 and what is the A2? And remember, this is a vector. So what is the component of A1? So we have to go up to this one and this one. So since it's a vector addition, so we have to find out the component. So look at that. So we have to go up to this one and we have to go up to this one, right? So A1 is actually this one plus this one. So this component, X component of this line plus Y component of this line. So it's a vector addition, no? So we can find out. Now the question is, from here to here, we know this is A0. Now we don't know from here to here what is the distance. Now how to find out this distance is easy. So let's name it. You name it x2 by x2 and this is x1. Now we really, and x2 is nothing but A0. Now let's x2 is nothing but A0, right? So how to find out? So we need to find out x, because x plus y is equal to A1. Simple vector addition. So what is x1? So x1 is actually cos of 60. So this angle is 60 degree, cos of 60 degree. So base. So this is my base. Okay. And from this carbon atom to this carbon atom is A0. Okay. So we can find out what is that. So you'll get x1 is A0 by 2. So this portion is actually A0 by 2 and this is actually A0. So total is actually 3A0 by 2. Now you know from here to here is 3A0 by 2. Now we need to know what is that Y component. So sine 60 degree is Y by A0. So Y is equal to A0 to root 3 by 2. So this portion also known. So then you can find out A1. A1 is the addition of from here to here, that is 3 by 2 into A0 plus whatever we have getting A0 into root over 3 by 2. That is A1. Similarly, A2 is actually 3A0 by 2 minus A0 by 2. Because the negative direction, no? It's easily to understand. Fine. Now, so we have done all these things. Now what we have to do? Because we know the basis function, we know the unit cell, so we need to run the summation. Correct? So this is the summation we have to run. So we have a 5 component. Why? So you see, suppose this is my nth part. So nearest neighbor, this is one nearest number, this is another nearest neighbor, this is one nearest neighbor, this is another nearest neighbor. If you are okay, you can take another nearest neighbor, this one also. But that component, again I am telling you that contribution is very negligible, so I have neglected it. If you are okay, you can also consider it. It doesn't matter. Now let's because we have to find out, as you know, the formula is MK B cos B matrix, and which is HNM B cos B e to the power IK dm minus dn. So what is the MK matrix? So like and things everything we had discussed in the earlier lecture. So we know what are the things that we had discussed. So we have to do the summation for 5 components. So 1, 2, 3, 4, 5. So first components actually we are doing summation of. So let's represent it n. This is my nth component. Suppose it is n, and let us do the summation of this component itself. And now go back and check your hydrogen molecules. So you have a 2 hydrogen atoms. When they try to form a hydrogen molecules, what are the matrix component? We know the diagonal is epsilon and the cross diagonal is t by t. So we know that part. Okay. Now what's about? Suppose this is my first component, first unit cell. Okay. So and this is my nth unit. So now we have to find out the matrix component, this one. So I have writing nth unit cell, and it has a 2 component A and B, 2 atom A and B. Similarly, first unit cell, which is a component A and B, right? A and B. Now look, A of nth so this component, if you see this component, so A of nth component is multiplying of A of first component. So from here to here, so that contribution you can neglect. It's far away from each other. So we can neglect it. As we know, so if you have a wave function from here and here, it is a far away. So definitely the contribution is very, very less. We had a multiple discussion on it. So that is why it is 0. So other component, similarly, the NB component corresponding to B component of first matrix. So that is also far away, so we have neglected. Now suppose B component of nth matrix is is actually acting on first component, A component of first matrix. So that you see this is very nearest neighbor, and the component of this attraction or this relation, let's represent by T. And how to find out the T component, that we already had a discussion. So D, like that. And what is the phase factor? Because you know from here to here it is actually A1. So we have written A1. With the same way we need to find out all the matrix. Okay. So 1, 2, 7, 3 part, all this part we have find out. So you see that we have 5 components, we have done all the matrix part. Correct? Now it is simple matrix addition, and if you do the matrix phase, you get a diagonal part 1 and you get a cross diagonal part. Now you see the nice part here. This one and this one actually complex conjugate, minus and plus, so complex conjugate. Okay. Now what is actually the EK diagram? So let's represent the whole part. This part means this whole part by H. So this is H and this is complex component of H bar. So that's okay. And what is the eigenvalues of these things? So epsilon plus minus H bar. So you can calculate. So here you remember H is actually, it is actually magnitude plus minus H magnitude. So because it's a complex conjugate. So if you are okay, and if you go to the view of literature, people end over here. Okay. Because this is nothing but my EK diagram, right? Energy version, and H is nothing but IK2 and K diagram. Because the problem is that it's not always the end, because if you go through all the literature, they also move forward based on applications. Okay. Since we are looking for electrical applications, so we can do some simplification over here further. And what are the simplification we are doing? Let's try to understand. Look at this part very carefully, and here actually I like to draw something. Here, you know, when you just go back and you see epsilon plus minus H means, right, epsilon plus H one component, epsilon minus H another component, means you have a, if it is, so you have a one component which is nothing but epsilon plus component. Similarly, you have another component called epsilon minus H. So that will always actually appear in double, right? So, and okay, and these things actually we are actually somehow looking for. So what is our goal? Our goal is to find out EK diagram for energy and K plots we will have. Now the question is, and it is always having doublet, correct? So suppose E plus K, so this is my, so suppose I write, so I think I should, so here actually let me write few things here. So here actually what I'm trying to see, like you have a epsilon here, suppose you have a, suppose this is my epsilon here, and you have to have go to further down, further up, okay, H, or further down, right. So this is my one. So this is actually what I'm trying to understand, that this is my overall structure. So if you try to find a EK diagram, suppose it's an arbitrary part. So you have some epsilon, some energy, and over that there is one energy state up and one energy state down. Thing is that, as you know, we are very much careful, we are very much interested those energy states which are very, very close to S. That is my the probability of occupation. No, like you had already, I've shown you, no, that for current flow, those energy states are those energies are very close to F. Those things are very much, we are actually very much interested. Correct. Now another thing is that, which are also very interesting, like the position of K. Okay, so now if you go, so that means we are, if you add plus H, so you will go up of this much amount, or if you add minus H, you will be very close to F. That's the idea. Now what? So but suppose we are interested those energy states which are very close to my F position, or that means my what is called my Fermi level, or chemical potential, very close to chemical potential. Now in that case, okay, so we are very much interested of those facts where the H components are very much zero, because look at that, if the H component is very high, it is farther up or it is very farther down. Either it's a very farther up or it is farther down. So which is not a good idea, right? So I don't know whether it's clear or not. So let me just tell you once more and how I'm trying to just convey this information. So this is very critical part. That's what I just make sure that you understand this part. One thing is that when people try to understand, and when people have taken first principle study, and when people have done lot of experiment, they found that, so epsilon, suppose this is my epsilon value, okay, this is my epsilon value. So if you add H over here, so you will go very far away from that F position, right? So this is the one energy level, so which we have writing a epsilon plus K. Or if you go adding something less, so that is also far away from the F, because that is actually F epsilon minus K. So the moment you add plus K or minus K, you are always going out of that very close to my Fermi position. Now my question is, why this epsilon? So this position is actually epsilon position. So why my epsilon position is very close to F? So people have find out, when people did lot of experiment studies, so they find out that epsilon position is very close to F, and so that is actually quite right. Why? Because look at that, look at that scenario very, look at that, like when we form the band diagram, you know that there is a upper some energy state and there is some lower energy state. There is some upper energy state and there is some lower energy state. And middle is called the intrinsic level, like, right? So lower energy state always filled and upper energy states is always empty. And this F, in ideal condition, this F is the middle, always flow the middle, the half. So you know the half probability, right? The probability of occupation half, that is the ideal condition. So probability of occupation, that means the upper states always filled and lower states is always empty. Sorry, upper state is always empty and lower state is always filled. So here you see the always lower states, you see always all electron try to occupy always lower states down to this state, and all the above states all actually empty. So definitely the probability of half, if you see, that also passes through the middle of this epsilon plus k and epsilon minus k. Similarly, the k. So k is actually the momentum vector or whatever. That also actually symmetrical. That you know, no? Epsilon plus minus k, or sorry, it is actually h, not k. So let me. So this is. Don't confused. So k, if you see carefully, like it is actually symmetric. So whatever so even if you go to if you go to my previous lectures, you see whatever the states are appearing top, the same amount of states are appearing below. So that means k is also passing through the middle. So it looks like that F and k are more or less passing through the middle. That is why I have written F and k in the middle. Okay. So F is the probability of occupation half. So that means if below all energy states are filled in ideal condition and all the above energy states are actually empty. So definitely F will pass through the middle. That is EF. EF is equal to EI. So that we represent the intrinsic condition EI. No? That's probability of occupation half. That means it's EI. So that's what I have written, F and K more or less middle pass. Now, as you know that we really need to understand those, or we are really interested, those energy states are very close to F. Now, what are the energy states that are very close to F and how to find out? We can find out if we don't go up or if we don't go down. So we are going up by H or we are going down by H. So if you can somehow make H is equal to 0, that means we are very close to F or K. Remember, F or K always in the middle is not trivial. Because if you doped it, it will vary something and something, it will vary. So in that case, we have to work it with other, we can work the previous EK diagram. Just one. You don't need to do much more simplification. But in the pure graphene states, it is better to start always pure graphene state. So if it is a pure graphene state, you know, if it is a semiconductor, your intrinsic state is middle of your valence and conduction band. And that's what I am saying. Similarly, the K, momentum is also middle. Why? Because it is a symmetrical. Whatever the states are appearing up, the same amount of states are appearing below. So definitely it is crossing. The K is actually in between E plus H and E minus K. So F and K both are actually kind of meeting, or they are actually passing between epsilon plus H and epsilon minus H. Now what we are interested, we are into those energy states are very close to that F. And how to find out all those? How to find out? Because if you can't somehow manage H is equal to 0. Because we are always going H is equal to H amount up or H amount down. So if you actually restrict H is equal to 0, that means we are actually very close to F. Maybe this energy state or some other energy state. So how to find out? H is equal to 0. Okay, and it's not about that always H is equal to 0. So H is equal to 0 or very close to the 0 point. Remember, H is equal to very close 0 or very close to the H is equal to 0 point. That are the energy states we are actually very much interested. So this is the things that we are telling about. This is A1 and this is my A2. So let's represent A1 x and 3 A0 by 2 by m and A0 root over 3 by 2 is equal to n. Same thing for here also. Okay. Then this is actually HK. Okay. So that HK matrix that we just now we have calculated, and what is actually our original EK diagram, E plus minus HK. Okay. So if you are okay that you can start with, you can retain E plus minus HK, but people have done lot of more simplification further with these things. So and this we have taken one of these eigenvalues like a epsilon plus H. Okay, so I am talking about H which is positive. So 1 plus e to the power ik1 e to the power ik2. Okay. Now what is IK1? So K means, since it's a graphene is a two-dimensional material, so Kx plus Ky. And A1 is equal to A1. So what is A1? Xm plus Ny. Xm plus Ny. So Xm plus Ny, and do the dot product, you will end up with Mkx plus Mky. Similarly, IKA2, if we do the dot product, we will end up with minus. Okay. So that means you have a H matrix. After rewriting all this, the IK1 looks like this one, and IK2 it is look like this one. Okay. Okay. Now, so that now IK1 and IK2. So we find out IK1 from this expression, and we can find out IK2 from this expression, and that we actually need to sit over, put it over here. What we will get? We will get this expression 1 plus 2 e to the power Imkx cos nky. Okay. Now, as I told you, we need to find out. So we need to find out the values for which Hk is equal to 0. As I told you, Hk is equal to 0 means the energy states are very close to my very close to my K values or S values, chemical potential or Fermi direct, my Fermi possibilities, very close to that. Now how to do that part? So let's plot Kx and Ky. Now it is a two part. This is 2 is there. So let's make Mkx is equal to 0. If you make Mkx is equal to 0, e to the power 0 means 1. So that would be 2. And but if you want to make it 0, so we have to convert it to actually minus 1. So that is nky is equal to 2 pi by 3. So nky 2 pi by 3 means, what is the value? It is actually that half. So half minus half. So minus half means minus half into 2 means minus 1. So plus 1 minus 1 0. So Hk is equal to 0. So that's what everything 0 2 by 3. Similarly, other component you can find 0 2 by minus 2 pi by 3, but it's okay. Because I have not written minus, you can write minus because since it is actually negative axis, y axis, so I have written plus. But if you are okay, you can put minus, there is no issue. Okay, that's up to you. Okay. Now, as I told you that it's not that, so we need to find out the values for which A is 0. So we have find out two values, A is 0, it's actually that simply symmetrical values over there. Not only that, so 0 or surrounding we need to find out. So one thing it is 0, or what are the surrounding values for which it is 0. 0 or what are the surrounding values for which it is 0. So it is actually like that. And you know, so if you have something, some function over here, and if you try to, and you know that this value is 0 for 0 into 2 pi by 3. Okay, this function is 0 for 0 and 2 by 3, these coordinates. So you can expand it Taylor series, so you will get not only this value plus surrounding the value for which the function becomes 0. Okay, so it's like that. So how to explain the Taylor series? So this is my Taylor series, H0 2 pi by 3 del h by del square kx. So first order term we have taken, you can use second order term, no issue. And this value already we have taken is 0, no? This value already taken is 0. This value is already taken is 0 because that is what we have done just now. So where 0 2 pi by 3, no? This function, so this is my function, no? hkt 1 plus 2 to the n. So if you put 0 2 pi by 3, it will be 0. That you know. Now if you do the first derivative and do all this exercise, you will get it is im kx. Similarly, kx 2 pi by 3, you will get 2 pi by 3. Similarly, finally, what you will get? Finally, you will get h is equal to imt kx minus ib. Now beta. So what is my beta value? So this is my beta value. Beta value is ky minus 2 pi by 3. So look at these things carefully. So what we have done, we just, because we need to find out 0 value, so instead of directly, so it is 0 value, this function is 0 here. This means so this function is 0 value. This function is 0 value, but what I am trying to understand, what is the surroundings? So how to do that? How to calculate this surroundings? You expand it by Taylor series. For the same function, for the same coordinate like 0 2 by 3, so this function will also give it. So it is not absolutely 0 value over here. You are also explained very close to that part. Okay. So that means you have energy states very close to, you have energy states very close to F. So all the energy states we are actually considering. So you have a particular point that is 0 2 pi by 3, and with this point we are actually went little bit ahead, little bit out, and see the other values. Okay, so that's what the Taylor series gives us. So and beta qi by 2 pi. Now it is h is equal to imt kx minus I beta, and you know that what is my eigenvalues? Epsilon plus minus of h. Now since it is a complex number, what is the way to find out complex magnitude of the complex number? You know. So finally you will get, this is my eigenvalues, right? So this is the eigenvalue. Sometimes it's reported in your whatever the papers that I forwarded. Now this is, I am ending over here, and whatever is written on that papers, please read all these things carefully, and that is the properties of graphene. People are using this graphene for a lot of application, and based on the application that you need to work on it. So for our application, I have taken h is equal to 0 for those type of things, but for optical, for mechanical application, they have a different argument. But whatever is that, so the most important part, this is my, so if you are okay, this is my eigenfunction, so that is correct always. Only thing is that we have done some simplification, and how we have done some simplification, we are actually considering those energies values are very close to F or K, and to have such a things, we have to make h is equal to 0, and to have h is equal to 0, so we did some exercise and we got some numbers, some cos ky and all these things. And not only that, we also expand this h with a Taylor series, because it's not like the absolute value of 0 or actually point value. We also go ahead surrounding of this point and try to find out the function, that energy values of E, and how to go little bit ahead of surrounding of H. We just expand all these things by Taylor series, and then we put all this Taylor series at this point. that 0 2 pi by 3, and then we come back and we found out the H matrix. And now you see epsilon plus minus H, magnitude of H, and if it is a complex number, how to find out magnitude, right? Under root x dot x bar. X bar is actually complex conjugate of these numbers. You will get all these numbers, and this is my eigenvalue. Again, I am telling you that if you are okay, then you can end it over here, and based on your optical, mechanical, or whatever application, the special condition you can apply. Here we have applied special condition because we are very much interested those energy states very close to K to calculate our current through the channel. Okay, so I'm stopping over here. Hopefully you have understood all these things. It's very interesting, and please try to read all this paper, carefully listen my videos, and if you have any problem you can drop a mail. That's fine. Thank you.